Okay, welcome back to Lighting Essentials. In this case now we're going to talk about lighting applications and about textures, which I mentioned at the beginning of the last lecture. So once again, I'm relying on the architecture of light to help make these distinctions, but I think they're very helpful. There are 4 levels of light texture: a very directional light, a directional light, a diffuse light, a very diffuse light. You can see it's something along a spectrum. So we take a look here, and this is a parabolic reflector, a mirrored reflector light, and it's creating a very directional light where we get a very strong pattern against the walls. And so that is one example of a truly directional light. Directional light, it's a little bit softer here. In this case, it's a floodlight, actually probably a wide spot. And it's creating, those very noticeable kinds of parabolic shapes, but it's a bit softer than the last example we saw. Diffuse light, we're beginning now not to really see the pattern of light at all. In this case, this is using a pretty wide floodlight to create, we can still see the pattern of the light, but it's quite diffuse. And then finally we get into very diffuse light, like the stuff we see in classrooms, the typical fluorescence. And in fact, these are a lot like the direct, indirect fluorescence that we have in our classrooms at community college. The shapes of light that we can create: pools of light, planes of light, and lighted objects. So think of these as your basic design elements. So here are pools of light where we create these different shapes, in this case from a fairly direct fixture. Here, where we have recess, cove lighting, and in this case most likely strip fluorescence, we can create a plane or lines of light that define the edge of this rectangle in the ceiling. Another piece is to actually make the object itself illuminated. In this case, it's both illuminated and it's illuminating the wall in these translucent wall sconces. Locations of light sources, so both their location and where they're shining. These are all the different kinds of combinations we can have. The most typical is ceiling to wall, but we can have more unusual things where we have from the ground upwards, from the wall upwards, from one wall to another wall, from a cove to a surface, a glowing source, and a low lighting to the floor, like step lights. So here we have ceiling to wall, and here we're creating a really rich texture. There was already this texture in the wall, and the fairly direct source is creating a richness of that wall texture that wouldn't have existed if we were using a diffuse light. This is the most typical arrangement where you would be lighting from a ceiling to a wall. But you can light from the ground upwards. This can be a little tricky, particularly in outdoor applications, but you can definitely defy expectations and create some very beautiful lighting effects. Another one, here are sconces, which are lighting from the wall upwards to the ceiling, and a little bit of light coming down. Here, lighting a wall-mounted fixture, a sconce, lighting the wall. Here, cove, the recess, lighting a surface. Here, glowing sources, objects that are illuminated from within. And here, low lighting on the floor. So these are basically the combinations of what you can do with lighting in terms of its location, where it is, and where it shines. Most of the time, that's not completely true. We're going to be in the ceiling. Why? Because the ceiling is the place that is least interrupted by all the other elements. It's where we can also mount all of the electrical supplies, and it isn't. But I would say 80 to 90% of most lighting takes place in the ceiling and is sealing from the ceiling to the wall or to the floor. Okay, let's talk a little bit about daylight. Daylight has a lot of advantages to it. It's free. So that's one thing. It's pleasing. It's got, what does it have? A full CRI of 100. So it has very good color rendition. Two flavors of daylight. Functional daylight, where we use it in space to serve as a general lighting, or we can also use it more dramatically as accenting to inspire moods, create visual interests. And the beautiful thing about daylight, well, particularly accenting, is it can be dramatic and change through the day. So we have different kinds of daylight. We have direct sunlight. We generally don't want direct sun coming into our interior spaces if we can help it. It's really bright, it has a lot of glare. What is glare? It's simply unwanted light. And we want to avoid that whether we're using natural light or artificial light. We can use a skylight, which brings in lots of different qualities of light, overcast, as well as skylight reflected off of the sky. And the diffuse skylight uses a diffusing material to manage direct sunlight. And we often want to use that, even though it can be nice to see through and see the skylight. Excuse me. So our site layout and massing is going to make a big difference about what kind of light opportunities we're going to have. The building's going to provide opportunities for glazing. Latitude determines the position of the sun. And we want to think about all of the forms of daylight, when it's sunny, when it's cloudy, winter, summer, morning, afternoon. It is one of those things that is a dynamic and changing force. When they built community college, among other things, they found that daylight was really annoying. That's why we have all those windowless classrooms, because they wanted to control the light. However, we realized that daylight and views to the outside world are really essential to our well-being as humans. So here's a very simple application, a wall window that just allows a flood of light to come into this space. A slightly more refined solution is a light shelf, which we see here, where the light is deflected, bounces off the ceiling, and relatively little direct light comes into the space. So it bounces off the ceiling and illuminates the space overall. We also can have high windows that we see here, clerestory windows that go way back to particularly very early churches and Roman buildings, but actually even back to the Egyptians, that allow usually a soft, unchanging light to come in. That's typically, but not always, very diffuse. We can have pop-up light monitor like this, which is essentially like a shielded skylight. And we can provide shading, both vertical and horizontal, to prevent particularly those low rays in the late afternoon that can heat up a building. Top light systems, skylight, or a bounce skylight, or a shielded skylight. So here's a plain old skylight we see through to the sky. We get both direct light, we get the view of the sky, but often we want to bounce the light. So here it is, there's light, there's also diffusing surfaces on the interior that bounce the light back. Here we have a shielded skylight that is creating a very dramatic effect at these joints between the ceiling and the walls. Okay, now it's time. Light calculations. So you need to be able to do very basic lighting calculations, and let me just give you a little bit of background. When I worked as a lighting designer, we did a lot of very simple, straightforward calculations. There have to be very complex calculations, but we can simulate those, we can do those in a lot of other ways. So you'll still want to be able to do relatively simple, straightforward lighting calculations. I'm going to go over two types. There are more, but these one type in particular may very well be, almost certainly, you will have to do a calculation on the final exam. Sorry to break the news to you, but that's the case. So, go back to lumens and illumination. A lumen, it's number of lumens hitting a surface, exitance, number of lumens coming off a surface in all directions, luminance, the lumens of light leaving a surface in a specific direction with a specific density. That's what we're really concerned about, luminance. So here's a diagram of that, and we can measure illuminance in foot candles, and we'll get a diagram of foot candles in a few moments. So the simplest calculation, and one that you will use, is really a rough back of the envelope calculation for typical spaces, residential interiors, open offices, classrooms, spaces that aren't really unusual as far as their characteristics. And basically we want to achieve a certain level of foot candles, and that's the number of lumens that are generated divided by the square feet. So all there really is, it's really addition, multiplication, division. I hope you're not too scared. It'll be okay. So, we solve for an illuminance level. We have 4 recessed downlights that each are, where they're incandescent, each generate 1,000 lumens, each 100 watts times 10 lumens per watt in a 12 by 8 room. Throwing a lot of numbers at you, but typical situation where we have this. So we have 1,000 lumens each. We have 96 square feet. We generate 4,000 lumens. We divide 4,000 lumens by 96 square feet, and we achieve 41, a little over 41 foot candles. By the way, that's fairly bright. The brightest you usually need to go for detailed work, other than say surgery, is 40 to 50 foot candles. So this would be a maximum brightness in a space that you would typically go. For a thing like a car door, you'd go down to maybe only about 5 foot candles, and there are all levels in between. But a residential, typical residential levels are between 5 and 50 foot candles. I hope that helps. So we solve for the number of fixtures. We know how much illuminance we need in a room. In this case, we need a lot. We need a lot of brightness. So we need 60 foot candles of illuminance in a 12 by 8 room. That means we have 96 square feet like we had before. We need 5,760 lumens. If we continue to just generate 1,000 lumens per lamp, we need, and I'm sorry for this misspelling, we need 5.7, we always round up, 6 luminaires. Not luminaries, luminaires. I thought I caught all these, but forgive me. There are other factors we have to bring in when we do this kind of calculation. So you can see the math is not hugely complicated. Multiplication, division. We have to also put into effect 2 other factors, which is light loss factor, which accounts for the performance over time, in that fixtures, typical fixtures, light sources, decrease in averaging over time as far as how much light they put out. We also have to correct for coefficient of utilization, a mouthful, CU, which is how well and how effectively the luminaires interact with the space to deliver light to the surfaces. How much light is lost to the surfaces. So that is factors that we want to work in. So to account for light lost over time, the industry standard, and this is typically for fluorescence, actually LEDs have some light loss over time, but not quite as bad as fluorescence. Meaning average lifetime, it's going to be about 85% as bright as when it was initially installed as the system ages. Coefficient of utilization accounts for the type of fixture and the light loss as it reflects other surfaces before it hits the object that's going to be illuminated. So these coefficients of utilization, a direct fixture, pretty efficient, shining light directly onto the surface. An indirect fixture, not so efficient, bouncing the light off a ceiling so that it illuminates walls and a floor, 50%. A spot or accent light that's really focused on a specific surface can get up to 95%. At least that's how we'll calculate it. And then a diffuse or ambient light, like a typical fluorescent fixture, we're going to talk about 75%. So let's take a look at a few examples. Here, there's a couple solutions, but we'll get to this a little bit later. For this pendant over a table, this is a fairly direct light, and we would actually want to do a point calculation to make sure we're getting enough light on that table. Here, however, with an indirect fixture throughout this space, we would use the Lumen method and use a coefficient of utilization of 50% because they're indirect fixtures used throughout. Here, in an art gallery setting, you would need to solve with a point method that takes into account the angle of the light hitting the wall. That involves trigonometry, and that's beyond the scope of this course. Know that the method for calculation exists, but that we won't be doing that. It will not be on, this will not be on the test. And here, another one. This could be also solved with the lumen level for this open office, in this case a direct fixture. So those are some examples of what you will typically come across in lighting situations. So we include these safety factors, the illuminance and the lumens generated. So we need to generate. So we multiply the lumens, in this case, by the light loss factor and the coefficient of utilization over the area. So it means essentially we're going to have to put in more lights than we did when we just did a raw calculation without taking these two features into account. So a point calculation calculates the amount of light hitting a specific object from a directional luminaire. Measured to the center beam candle power, the area of a pool of light which has the highest density of light, the brightest spot. And illuminance, the candela value, divided over distance squared in feet. This looks scary, doesn't it? Sorry. A pendant fixture hanging 3 feet above a table with a center beam coefficient power of 2200 candelas is 2200 candelas divided by 3 squared equals 244 foot candles. Bright, quite bright. Because light decreases with distance. This is a bright pendant very close to the surface of the table. So this is another candela value, illuminance times distance squared. And this way we can solve for it, and that we would be generating 100 foot candles times 3 foot squared equals 900 candelas. When the object is not perpendicular to the light source, the light spreads out and is less effective. Therefore, the calculation is to take this into consideration. Candela value needed equals lumens desired times distance squared divided by, oh my gosh, trigonometry, cosine of angle. Simply know that these exist rather than worrying about having to calculate it. So in order to get some of this information, we need to go to cut sheets. You'll be doing this a lot in lighting design of individual fixtures. Here's an LED recessed fixture, and here is the photometrics. And you can see it's very pointy. It's a fairly direct piece, and this is showing us the lumens. If it was a more indirect fixture, we would see a much more rounded shape. So we can pull the candelas off of this. And also we have coefficient of utilization. So here's the candle power at different angles with maximum candle power straight down and less as we move along. Okay. So this is where we look at it more closely and where we can pull our numbers for doing the Candela distribution. So that was a really rough overview. Know that these exist, but that actually the only calculation that I'm going to be having you do is the very first one, which is the Lumen method, but you will have to think about coefficient of utilization and light loss factor. Okay, there are other calculations you do for eccentrically shaped spaces. We do less calculations with that, and we do more lighting simulations when we start getting into complex spaces. And those include room cavity ratios and other more elaborate calculations that you'd use for something like the coffee house in the Winnett building, or the cube in the pavilion building. So that was a really rough overview of calculations. I hope you're not completely frustrated and confused, but this is where I'm going to stop. So, wasn't that fun? I hope it wasn't too bad. For the test, you'll only probably have to do one calculation. I'll provide the formulas and even the light loss factors, but you should have a calculator ready. You'll be taking them at a computer, so you can use the computer. I use Excel spreadsheets a lot when I was calculating light levels. So that's it. That's the lighting basics. So these two videos are the videos that you need to watch. So thank you. I will be producing lectures for the remainder of videos of the remainder of the lectures, but these are the ones that you should know. All right. Over and out.